use or reduce quantum yield.
Okay, thank you, Anastasia. The next speaker, Dmitry Spasskiy, online speaker, online speech talk, and his presentation, Luminescence properties of xScxPO4 solid solution.
Добрый день, уважаемые коллеги. Слышно ли меня?
Слышно.
Слышно, спасибо. Сейчас я попробую запустить презентацию. Видите ли вы презентацию?
Да, видим.
Так, и вторую страницу тоже, да? То есть она перелистана.
Да, начинайте.
Хорошо, спасибо. Thank you. So I will try to make my presentation in English just because I see that our international audience is interested in presentations. So first of all, I want to thank the organizing committee for an opportunity to make an oral presentation at Philo Symposium. This is my first time of participating in this symposium. And I also want to apologize for any inconvenience which are connected with urgent transfer of my presentation from offline mode to online mode. So, but in this case, in my case, it allowed to the symposium to get at least one COVID positive participant. So let's start with my presentation. It is entitled Luminescence Properties of Yttrium-scandium Phosphate Solid Solutions. I want to start with the motivation. So we will focus on the UV emission of these solid solutions, and I first want to talk about the possibility of application of compounds which emit in UV spectral regions. So there are different areas of applications such as scintillating detectors, UV disinfection, photocatalysis. Also medical applications are possible. We can virtually divide UV region into three regions, so-called UVA, UVB, and UVC spectral regions. So with a little bit different properties when we are talking about, for example, bactericide properties. So here I want to present a pretty nice example of possibility of killing of some bacteria with the light of different ranges, UVA, UVB, and UVC. So you can see the dependence of the killing possibility via the dose of UV radiation, and UVC emission is the most efficient in this case. Then UVC phosphors are also attract attention due to possibility of their application in medicine. For example, it was shown that UVC emission allows killing superficial cancer cells without damage to deep tissue, because UVC radiation does not penetrate deep into the tissue. So when we are talking about the phosphorus which emits in UVC range, and this range, I forgot to say that this range is from 200 to 280 nanometers. So when we are thinking about possible phosphorus which will emit in this spectral range, we are talking usually about wide band gap materials such as phosphates or borates, usually doped with different rare earth ions, which gives us emission from 5D levels to 4F levels. So 5D levels are highly influenced by the crystal field, so the energy of these levels can be shifted in a wide energy range, thus giving us possibility to get luminescence from these ions in a wide spectral range. When we are thinking about compounds with intrinsic emission, so they are usually out of scope of interest, especially when we are talking about UV emitters, just because intrinsic emission usually suffers from quenching effects at room temperature. But we can hope that solid solutions can help us because when we go to solid solutions, we can get some effects such as enhancement of luminescent thermal stability of the luminescence emission, as well as another point in which solid solutions are benefits is the possibility of enhancement of light yield from such kind of compounds. So I will present our study of the luminescence properties of undoped yttrium scandium phosphate solid solutions. And there are generally 3 points from which we started our studies. So first of all, I want to say that we knew that in principle, phosphates, in particular scandium phosphate, can emit in UVC regions. So the emission band is around 200 to 210 nanometers, but the emission is seriously quenched at room temperature. Then we have performed some studies before, but with samples doped with europium, and it allowed us to detect UVC emission even for such kind of solid solutions, but it was again low temperature. But the main interesting point for us was that the difference in band gap values of the constituents of solid solutions, namely of yttrium phosphate and scandium phosphate, is very large. So it exceeds 1 EeV, and when we are talking about the difference of the states of the conduction bottom, which are formed with yttrium or scandium states, it is as large as 1.5 eV. I want to say now some words about the novelty of this work, also taking into account our international audience, because for some time we thought that no one tried to study these rather simple compounds. But recently we found very brief, very short paper. So here is it, only 1 page, and coursership here is, as you can see, it is coursered by Oscar Malta. So there will be one question to Professor Malta. I could not find any other papers from you concerning this topic, so maybe they're published somewhere which is not available in internet, so please share them with me. But anyway, I can say that we got absolutely different results from that you have published here. Okay, and let's go to the results. First of all, crystal structure of rare earth phosphates crystallized in two structural types depending on the cation. So for the cations, for the rare earth cations from lanthanum to terbium, it crystallized in monazite structural type. And for other representatives of lanthanides, as well as for yttrium and scandium, the phosphates are crystallized in xenotime structural type, which is characterized by the coordination of phosphorus by 4 oxygen atoms, thus forming distorted PO4 tetrahedron. And for rare earth atoms, so it is 8 coordinated, also somehow distorted. And when we are talking about yttrium and scandium, for scandium, the octahedra is a little bit more distorted. Okay, so both of these compounds are crystallized in the same structural type, so we can hope that the whole set of solutions will also have the same structure, and that's what we can see from the studies, from XRD studies. So all samples which we are studying with single phase, the unit cell parameters decrease with a substitution of yttrium by scandium, which can be explained by smaller ionic radial of scandium in comparison with that of yttrium. So generally, the dependence of lattice parameters can be fitted with a linear function, but we can imagine that there is some deviation from linear behavior for the compounds with low scandium content. Let's go to the luminescence. I want to present the luminescence spectra of the solid solution. So it's equal ratio of yttrium and scandium in the solution. So we can see two prominent peaks around 2.7 and 5.2 eV. However, if we will try to decompose the spectra into Gauss curves, Gaussians, we will need one more curve, so peaking around 4.5 eV, and it is reasonable as we can see from the excitation spectrum. So if we will go to the low energy slope of the high energy band, we can see that its excitation spectrum, which we believe belongs to this band at 4.5 eV, it is absolutely different from that which we can get in the maximum of the UV emission band. Generally, we can suppose that two low energy bands are associated with some kind of defects, while the high energy is of intrinsic nature, just looking at the excitation spectrum. So we have a non-set in the region where we can expect the band gap for such a high band gap compound. When we will look, if we want to look to the luminescence spectra of the whole set of the studied solutions, we can see that this UVC emission band can be observed for the whole set of the solutions except the phosphate without scandium for yttrium phosphate. So even for the lowest concentration of scandium, as low as 1%, only 1% of scandium, so this emission band dominates in the luminescence spectrum. So the band shifts with their change of composition. So from 5.95 eV, which is observed for pure scandium phosphate, and down to 5.2 eV for the samples with scandium content lower than 0.6. Uh, we have also studied the decay curves of this emission of UVC emission. So it was excited by pulsed electron radiation. We got rather complicated decay curve. We managed to fit it only using four exponential curves and one more which describes the rising part of the curve. So, but to get some idea about the decay times, I just want to share the data when the intensity falls in E times. So, and we can see that the emission is pretty fast for such non doped material. So it's a few hundreds of nanoseconds, and it goes down to 56 nanoseconds for pure scandium phosphate. Uh, Generally speaking, if we will talk about some other compounds with scandium, we can see that they also give us emission with rather similar decay times. So it allows the whole set of data, allows us to attribute this UVC emission band to self-trapped excitons with the participation of scandium states. Namely, so we suppose that electron component is placed at 3D states of scandium, while for whole component, as it's usually admitted in oxide, so it's oxygen state. Uh, what about the intensity of this emission? We tried to estimate this emission in two approaches. So first of all, we tried to measure the quantum yield, and the quantum yield was measured relatively to that of sodium salicylate, and we suppose that the uh, yield of sodium salicylate is around 64%. So we got a pretty nice curve for the UVC emission. So we got local maximum for the equal concentration of yttrium and scandium, and emission is rather intense. So it was 52% relatively to sodium salicylate, and it allowed us to estimate the absolute quantum yield as 33%. Here, I also want to say that the excitation wavelength was 174 nanometers. So this wavelength corresponds to the emission to transitions in xenon. So the potential gas which can excite such kind of phosphor. So another approach was to estimate the efficiency of energy transfer of high energy excitations to the emission centers. So we studied the emission intensity at excitation 45 electronvolts and tried to compare the emission intensity of one of the representatives of our solid solutions with 0.1 concentration of scandium to one of the most popular compounds now. It's gadolinium, yttrium, aluminium, gallium, garnet ceramics. It is shown that it can give us, it's a well-known, it's popular scintillator now, with a light yield up to 40,000 photons per 1 MeV. So we can see that the intensity of this UVC emission band is at least comparable with that we can get from such a good scintillator. So it allows to make conclusions that the energy transfer is efficient in our phosphates. What about thermal stability? So also very interesting results. When we are talking about scandium phosphate, we can see that the emission is hardly, is seriously, considerably thermally quenched at room temperature. But when we start to substitute scandium with yttrium, even 20% of yttrium gives us considerable improvement of thermal stability. And for concentrations of scandium lower than 0.6, so the emission is absolutely thermally stable at room temperature. And for lower concentrations of scandium, so we go to the high temperature limit of our measurements, 350 kelvin. So the experiments were performed with helium cryostat. We could not get to high temperatures. So the emission in such kind of samples is stable up to 350 kelvins. Uh, when we are talking about the emission of solid solutions and such kind of emission, so it is not unique. I want to say that for different solid solutions, it was shown that it is possible to increase the emission intensity, the light output for some intermediate values of substitutional atoms. And the theory which was proposed to explain such an increase is that there is a possibility of clusterization of solid solutions. So we can get some local areas in our compound which are enriched with one component of solution. So what it can give to us? So first of all, it allows us to localize the excitation. It allows to decrease the free mean path of the charge carriers of their travel, so they will be close to each other. So the radiative recombination of geminate electrons and holes will be higher in this case. So I need this introduction just to go to the excitation spectra of our study of material studied by us. So I told in the introduction part that there is a huge difference between the constituents of our solid solutions. Really, we can see the edges in the excitation spectra of the UVC emission of scandium phosphate, so the peak at around 7.5 eV, and for yttrium phosphate, if we'll study the excitation spectra, if we look at the excitation spectra of defect-related emissions, so we also can see a huge rise, which is connected to the interband transitions with a peak around 4.6 eV. So it very nicely coincides with the values which we can get from the literature, from the studies of Peter Dorenbos, and he provides us with a scheme how the states in the conduction band bottom and in the region of the top of the valence bottom, how the shifts this, how the energy shifts when we go from yttrium to scandium phosphate, and you can see that the gap, that the energy difference between the bottom of the yttrium and scandium phosphate is around 1.5 eV. So it is higher in energies for yttrium phosphate, and also the top of the valence band is also higher for yttrium phosphate. So I need this part just to talk about the excitation spectra, because if we have some solid solution, so for one we get band gap energy is 7.5 eV, for another 8.6 eV, we can suppose that for solid solutions, we can get some intermediate values. So we'll get gradual shift from lower values to higher values. It can be linear or non-linear, but anyway, gradual shift when we will change, substitute scandium for yttrium. But in our case, it was completely different, as you can see from the excitation spectrum. So we have no high energy shift when.
Sorry, Dmitry, move to conclusion.
Okay, I'm sorry. Yes, I will try to end my talk fast. So very unusual dependence of the excitation spectra, and we guess that such unusual dependence allows us to suppose to show the possibility of clusterization of solid solutions. We have performed some modeling for two cases for random distribution of cations, and for with a count of scandium correlation. So here is the distribution, here is the potential landscape, and you can see that we can get for the case of a count of scandium correlation some clusters here, and how it will modify the density of states in the region of the band gap age. So here is, I want to talk only about this picture, only about this figure, 1 minute, and I will finish. So in case of the absence of any correlation for scandium cations, so there will be a gradual shift of the band gap age. But if we get some clusters in our case, so you can see that it is presented with solid lines, the density of states are presented with solid lines, so there is almost no shift, and this is the case which we get in our experiments. So I will go to conclusions. We got some results on the solid solutions of yttrium scandium phosphates and have shown that we can get rather intensive emission in UVC spectral regions, which is characterized with pretty nice thermal stability and rather fast decay times. And we can suppose that the clusters which are formed with scandium states and deep energy wells which we get in these clusters are responsible for enhanced light yields and for enhanced thermal stability of UVC emission in these compounds. So thank you for your attention.
Thank you, Dmitry. We have questions from Andreas Mehring. Very interesting talk. The lowest excited state would be a triplet state with a spin forbidden transition. This gives a long emission lifetime at low temperature. Do you measure it?
So I can agree that it is it's really similar to normal obvious ligand to metal charge transfer, which is usually characterized with decay times in microsecond scale. Yes, so the first part of the question, yes, I agree.